Good morning, everyone. My name is Timothy Mills, and I will be one of your room hosts for today. For this session, running imagery and geospatial workloads in the cloud, we're going to be joined now by our speaker, John Hildebrandt. Please welcome him to the stage. Thank you.
Thank you. We wish to acknowledge the traditional custodians of the land we are meeting on, the Ngunnawal people. Wish to acknowledge and respect their continuing culture and contribution they make to the life of this city and region. I'd also like to acknowledge and welcome any other Aboriginal and Torres Strait Islander people who may be attending today's event. So good morning. Today I'll be speaking on some of the challenges in running imagery and geospatial workloads and how AWS can assist in this area. Hi, my name's John Hildebrandt. I'm a principal solution architect in our national security team based here in Canberra and work with a number of customers around town in that domain. So it's really great to be here in person at an event of this size. We've had several thousand registrations and I'm really looking forward to catching up with some of you and other customers throughout the day. So if you can think back, particularly those with maybe a few grey hairs, back to the time when we didn't have GPS in our phones and our cars and things. You used to have to get around, maybe struggle with street directories, for those that can remember those wonderful things, or maps as you travelled. Finding your way somewhere you didn't necessarily know what the weather was going to be like, the warning times for natural disasters could be quite short. Today, if you fast forward, fortunately we have the benefits of things like GPS in your car to help you navigate, or on your phone. We have great visualization and warning times to help literally save people's lives from, say, natural disasters with weather observation satellites. And in the military and intelligence domain, knowing where your adversary is or even where your own troops are, it's been a critical requirement, and it leads to a better outcome for you if you've got that visibility. And overhead imagery has been a critical component in that type of intelligence gathering. So in fact, this year is actually a milestone in this space of Earth observation and satellites. It was back in July 1972, so 50 years ago, when NASA launched what's now called Landsat 1. And so this was the first time that a dedicated Earth observation satellite was launched, which would provide full Earth coverage on a regular repeating basis. So the resolution of Landsat 1 was pretty modest by today's terms, 70 by 80 metres in pixel resolution, and it had an 18-day repeat cycle. So every 18 days it would go across the same part of the Earth. But this was a real watershed. It enables, for the first time, these global analysis tasks to be looked at, large-scale land masses, to be able to answer some important problems for a variety of different domains. And in fact, as well as providing a single band, it actually provided multiple spectral bands, which also assisted in doing things like land cover analysis and so on. If we fast forward, though, to today and look at what NASA has in its kit bag, it actually has a whole fleet of Earth observation capability. So this is just showing some of those. This is a variety of different resolutions, different spectral bands that they collect, not just electro-optical, but also things like synthetic aperture radar and different sort of spectral collections. Also, they're launching assets for different types of use cases. So it's not just about land observation, but oceanographic tasks, even some that are focused on looking at the cloud cover, which in the past clouds are bad, but there's some people that want to look and understand cloud cover, for example, in addition to things like the weather observation satellites. So a vast amount of sort of data that's being generated here in this constellation of satellites. And it's not confined to the US with NASA. If you look here, this is a similar sort of picture from our friends at the European Space Agency. So again, they have a similar collection of satellites with their Sentinel program, providing multispectral electro-optic imagery. They've also got radar-based satellites and weather constellations and so on. As well as those sort of government assets now, though, we've also got the additional aspect of commercial satellite constellations. So, and in fact, some of these are quite interesting and they start to get to the much finer resolution use cases. So whereas Landsat 1 was at sort of 70 by 80 metres for a pixel on the ground, some of these commercial satellites now are going down around the third of a metre or 10 centimetre type resolutions. So that enables, as you could imagine, that enables quite different sort of use cases. So rather than just maybe looking at ground cover, you can actually start to see things like cars and so on. Many of these platforms such as Sentinel, Landsat are actually making their data available at no cost. And in fact, many of those are storing that data on the AWS platform to make it broadly available to different customers across the globe. If we look at the sort of raw satellite launch numbers, this is just showing launches of objects over time. And you can see over the last few decades, it's been fairly constant, around a sort of couple hundred or so launches per year. But then if you look at the last few years, you see this real hockey stick starting to occur. So classic sort of exponential growth, where driven by things such as the lowering of launch costs, and also the use of much smaller satellites, so the sort of micro, nano satellite type technologies and constellations rather than relying on very large, expensive satellites. So we're seeing the numbers of collections really explode in this area. And this is generating a huge amount of data that you need to be able to process and store. So the kind of realities in this space then is, I think that's made it pretty clear. I've just talked about satellite-based collection, but we've really got this explosion of geospatial and imagery data, both within satellite collection, but also in a variety of other areas. So you think of things like UAV collections closer to the ground, or aerial collections are also growing in use. Everyone these days carries a mobile phone that can collect georeferenced imagery, and also even things like social media is collecting data, which is often georeferenced. This is leading to an explosion of different formats for people to manage, different types of modalities that you collect typically can drive different format requirements. Being able to optimise the storage to deliver over the internet might drive things like cloud optimised geotiffs, or you may want to process a stack of, say, spectral or temporal data and use things like data cubes, which you'll hear more about in the session after this. At the same time, while we've got this huge growth in the volume and velocity of collection, the time you've got to actually process that data is actually getting less. If you think back to that Landsat 1 example, you had that luxury of that 18-day sort of collection cycle. So the satellite went over, you collected one image, and then you had 18 days to sort of look at that before you got the next image of that point of the Earth. So that was quite a bit of time. Fast forward to today, some of these constellations are literally collecting data on multiple revisit times within the same sort of 24-hour period. And that's being really useful for some customers because they've got use cases that need that sort of frequency of data. One example there was given by a customer was they actually were using this data to look at the number of cars around the shopping centre. And because what they wanted to do is that was giving them an indication of if the shopping centre's busy, they actually need to get more logistics to get material into that shopping centre. And as you can imagine, so you need to have your data at a lot faster than 18 days. So how do we cope with this sort of vast amounts of data that's coming in and to process it and get useful intelligence from it? So this is just showing you the typical intelligence cycle that's used by a number of my customers. This is focused here around the imagery intelligence cycle. So it starts at the top there, where typically you have some sort of question you're trying to ask and get the answer for. That typically drives you to plan some sort of collection of information. And so you go through some sort of collection phase, where you may be using satellite resources, UAVs, or whatever in the imagery domain. You'll then typically collect that information. You'll need to pre-process that, get it in a form that you can start to do some sort of exploitation or analysis on that information. And then once you've done some analysis, you've got an answer, you'll typically want to provide that answer to your customers that want to use that intelligence. And that often then generates new questions, and the cycle continues. So what I'm going to do for the sort of remainder of this session is really focus on this intelligence cycle and the 3 steps that I've got in bold here around collection, processing, and analysis, and talk to how AWS can assist in those areas. So let's first start off with the collection and storage area. So collection, as you can imagine, leads to the requirement to store this vast amounts of information. So let's look at the satellite example that we've been talking about. So if you, these days with the costs of launch decreasing, people looking to lower cost methods of building constellations of satellites, they often are in a situation where, particularly if it's a startup or a small company, they may have the resources to launch some satellites, but that doesn't necessarily mean they have their own ground infrastructure. So they're not in the sort of NASA league there with their own infrastructure, which means they have to find a, say, third-party ground station infrastructure, negotiate access to that. Then they need to connect that through to some sort of processing and storage capabilities, and then a distribution network. And some of the feedback we've received from our customers in this domain is that that's often added sort of latency along each stage of this process. So the time to get their results out to their customers is sort of delayed by this process. It can also be quite expensive, to address all these areas. So that led AWS to develop the service to help customers in this space called AWS Ground Station. So this is just like all of our services, a pay-as-you-go, just pay for what you actually use. It's where we directly connect literally satellite ground station infrastructure directly connected to our regions across the globe. What this means is that you can downlink that data from your satellite or uplink instructions to it, and then quickly get that information into a resilient compute and storage infrastructure in your AWS region of choice. And we've seen that typically reduce the time that we've been able to get results to their customers. So as an example of that, this is one of our customers called Capella Space. They've actually quite an interesting sort of use case here. They've built a constellation of synthetic aperture radar satellites, so one of the first commercial providers to do that. So synthetic aperture radar is interesting because it, unlike electro-optic collection, it's not limited by being in sunlight. So it's day-night collection, 24-hour access. It penetrates cloud cover, so again, that enables a whole set of use cases for surveillance, even in the face of cloud cover. Many of those use cases, they wanted very timely access to their data and get it to their customers as quickly as possible. And some of the feedback they gave to us was that some of the traditional approaches, as well as being quite expensive, was actually leading to up to sort of 24-hour delay in getting their data through to their customers. And by using AWS Ground Station, they were literally able to get that down to minutes to get their data through to their customers. And in fact, another example from one of our other customers in this space, they actually did what you could call a satellite selfie to illustrate the sort of speed of the collection in this space. So one of our customers, literally they tasked their satellite to take a photo of their own facility. They all walked out of the building when they knew the satellite was going to go overhead. It took the photo, it was downlinked to AWS Ground Station. Literally, by the time they got back into the building, they were able to bring that picture up onto their workstation and see the picture of their team. So AWS Ground Station, it's located across the globe, directly connected to a number of our regions across the globe here, including in one situated in Sydney in Australia here. But you can make use of any of these ground stations, and that's particularly important if you're looking to get data as quickly as possible for the satellite. Because particularly for low orbit satellites, they've got a limited field of view of parts of the ground. So if you've only got, say, one ground station, you might be limited to only being able to collect data from it, say, once every 90 minutes. By having multiple collection points, you can get much faster access to your satellite. So that means as well as getting faster access to your information, it can also potentially reduce the need for things like onboard storage on the satellite. So again, helping to reduce costs there. With Ground Station, you can, while you collect the data at any of these points, you can then choose to transfer that data across our global private network, which connects all these regions to the region of your choice. So if you've got a requirement to aggregate all your data, say in Sydney, you can do that. So once the data is collected with a service such as AWS Ground Station, you typically want to collect that information in some sort of reliable and secure storage environment. So customers, the feedback we get is they typically want something that's scalable, cost-effective. They also want it to be secure and be able to control access to that information. So they want to be able to have the, to control need to know, but also importantly, provide the ability to share that information. So they need to share to the appropriately authorised people. There's often typically a requirement to support multiple different data formats. Different products have different requirements in that space. Different types of collections have different formats and so on. So you want the ability to be flexible in that space, not be constrained by a particular sort of product requirement. And then you want to be able to connect that store to a variety of different analytics tools. So it's not just sort of one analytics tool to rule them all. It's tools for choice. So you might have different tools for, synthetic aperture radar versus electro-optical, or ground-based collections and so on. So this leads to what we often work with our customers, this sort of data lake type strategy. We use something like Amazon S3, which is our object-based store, and then have a security layer around that and allow you to connect your compute resources to it. So this is really, it's kind of like a flip of the traditional sort of data flow in this place. So traditionally, there was often a lot of focus in this space. I remember, you get the tape drives and you collect the data and then carry it to the right, to the HPC environment or the processing environment or your high-performance workstation. So it's often a mental model of moving the data to the very important compute. That's kind of flipped on its head these days. The amount of data is simply too large and it's coming in too fast to be able then to sort of be wanting to shuffle it around. It takes too long just to move that data. So the paradigm today is very much around get your data in a secure, resilient location, something like Amazon S3, for example, but then be able to plug multiple different types of compute resources to it. So if you've got some software that, say, runs on a single server, you can use, say, Amazon EC2 here. If you need a cluster, you can use services like Amazon EMR to run up clusters of compute capacity, to run high-performance algorithms across that data. Or if it's, say, simply, maybe it's some geospatial tabular data, you might want to run a SQL query across it. You can use services like Amazon Athena to directly run SQL queries across that data within that, while it's still in that S3 bucket. Now, what if you if you're not blessed to own a satellite or have direct access to a satellite? Because I've been talking about using ground station and connecting. So everyone in the audience here may not have access to satellite. Does anyone have access to a satellite? In fact, put up your hand if you do. Oh, there's one. Well done. So for the rest of you, this slide's really important. So if you don't have access to a satellite, that doesn't mean you can't leverage the data. So many of these, particularly things like from Landsat, Sentinel, from ESA and NASA, provide that data at no cost. But like I said, it's a lot of data. Do you want to actually copy all that down onto your own sort of hard drive or laptop? That could be difficult. So we've actually made, through a program, if you go to our Earth on AWS website and our, what's called our registry of open data, you can actually search for data sets that we've made available on our open data program. And so at no cost, so we're paying for the storage there, you can get access to that data in an AWS region, so it's co-located with this compute resources that you can use to analyse that information and derive useful intelligence from it. Now, there's also commercial-based models with some of these satellite collections, and so in that case, we also have a service called Data Exchange, which you can make data available at no cost or on a commercial basis. So it's a great way if you want to manage data in that sense and make it available to your customers. So tying this together now, I want to sort of go through this an electro-optical imagery reference architecture. So the link on this slide will take you to this online, and you'll be able to get these slides after, so if you don't catch it right now. But this is really just stepping through that whole cycle and how these things start to tie together. So on the left here, we've got the satellite, and we're using AWS Ground Station. And so what that gives you the ability to do is to downlink that data. You can then install your own, say, software-defined radio stacks, your own processing, that if it's specific to your sort of satellite capabilities, your own encryption, decryption, for example, to get the sort of raw data from that, and then to transfer that to an S3 bucket. There's also the ability within Ground Station to just go directly to an S3 bucket if the processing we provide's sufficient. So that gives you that raw data from the satellite. There's typically what happens then is there's some sort of pre-processing steps that go on. So you might be registering it to a ground, to the sort of ground map projections, those types of things, correcting for atmospheric distortions and so on. And so this is sort of this pre-processing step. You may do some quick quality assurance or quick review of the data at that point too. And because of the speed that we're able to start working with the satellite, with Ground Station, you can start to have this sort of feedback loop here. And so, for example, if the image is collected and it's, say, there's no cloud cover and it's a good image, you might want to tell the satellite you don't need to collect any more of that location. Or conversely, if it is cloud covered, you might want to, say, retask and do another collection. Or, for example, if it notices something changed from previous collections and something interesting's happened there, you may want to, say, task the satellite to revisit at a higher resolution or even retask other assets, for example. The data then, that sort of analysis-ready data is then stored in typically something like an S3 bucket in that sort of data data lake type architecture. You'll often have metadata associated with these image collections, and you'll store that in some sort of database. So here I'm using DynamoDB as a NoSQL database. You could also use, say, a relational one there if you chose. There's often requirements to, say, archive this information. So you may not be using all of it immediately, but you may want to keep that data for historical records. And certainly NASA want to keep their entire, Landsat archive for many, many years. And things like S3 Glacier and Deep Archive are really useful in that space. The data can then be sort of further processed and perform analysis applications on it, AI machine learning algorithms and so on. And I'll talk more about that as we move on to the sort of analysis phase. And then you'll want to store product and disseminate that to the end customer. So I've talked about the collection and storage sort of phases. Now let's move on to the processing and exploitation area. So we've got this massive amounts of data, how do we actually get enough compute to be able to process this information? And so I want to mention one of our customers, Discard Labs. They had this challenge, and they were working on what they called planetary scale problems. So they're looking at the whole of Earth at different sort of in spectral bands, different resolutions and so on, and trying to solve problems at that sort of scale. So as you can imagine, that's a huge amount of information that they were dealing with, and they needed a lot of compute capacity to deal with it. So to prove that sort of AWS was a suitable environment for that, they actually went through the process of spinning up over 4,000 servers on AWS. So hundreds of thousands of cores that this represented. And they went through the top 500 process to actually put this onto the top 500 list. They got to position 40 on that list. And that's very impressive considering this was a small company. They did this literally over a few days, with quite, a modest expenditure. And in fact, if you look at that time around the top 40 list, some of those sort of adjacent ones represented some of those other top 40s. They represented millions of dollars of sort of sunk investment costs. So what does the sort of reference architecture for a high-performance computing workload look like on AWS? So what are the building blocks that you'd use to build up that sort of HPC capability? So there'll actually be a lot more detail on this in a following presentation later today from the Bureau of Meteorology, but I'll just go through some of these and give the basics here. So at the foundation, you need somewhere to store your data. So like I talked about, that using things like Amazon S3. So using that in a HPC context, you'd leverage things like its ability to use its parallel nature of its APIs, so you can get parallel high-performance access to the data in that object store. If you've got software that actually needs block storage, it's a maybe more traditional approach. You can use things like Amazon Elastic Block Store, and there's multiple options there to get very high-performance I/O capabilities. Within the HPC space, it's often very common to have some sort of parallel file system. Things like Lustre are very common, for example. These are very performant, but they're also often complex to set up and manage and maintain. So we've actually built Amazon FSx for Lustre to give you a managed Lustre parallel file system. Then you need compute. So there, things like Amazon EC2. So we've got a variety of hundreds of instances available, and many of those that are targeted at sort of compute optimized, as well with both CPU options and also GPU accelerated options in that space. You then need to have very high network performance in this space. So we've done things in this area to optimize that at the individual instance level with things like the Elastic Fabric adapter, but also for connecting multiple instances together. So within our virtual private cloud, we have what's called cluster placement groups to give you high performance networking capability. So then you've got your storage, your compute, your networking tied together. You've got the ability to build up that sort of cluster of compute capability. So you typically then need to manage that cluster, and there's often lots of different sort of software products out there in that space. So we have if you're looking at sort of a scheduling type model where you want to schedule jobs on that cluster, we have an offering called AWS Parallel Cluster. And we also have AWS Batch for more of a batch sort of oriented view of leveraging that cluster. You'll run your jobs on that then, do your analysis and get some results. You'll typically want to visualize the results from that cluster. So that's where things like high performance graphics workstations come in the picture. And that's often been a sort of expensive sort of undertaking in its own sense. So we've actually got methods. We have the nice DCV protocol and the availability to virtualize that and stream those sort of visualizations to a lower cost instance. So another example in this space using this sort of stack is from our customer Maxar. They've actually put this together to do weather forecasting, and they found they were able to deliver the weather forecast faster and at a lower cost. And I've got a link to that case study there. And like I said, later today you'll hear from the Bureau of Meteorology as well. So now I've talked about the sort of collection and storage and the initial processing of data. What about the analysis, actually doing the intelligent stuff, getting understanding out of this data you're collecting? So we've got this massive amount of information, and we're really getting to the world now where we literally have more images are being collected than we've got humans and time to look at all of those. So in the past, if you took a photo or collected an image and no one looked at it, it was kind of wasted. Now we're in that world. We need to get beyond sort of just having humans on task. So there's been a lot of interest in and growth in the use of automated processing, AI and machine learning algorithms to try and help augment the work of the analysts. So trying to flag particular images for them to look at so they can do the high value tasks on the data of interest. Now that sounds great, but the problem here is that building artificial intelligence and machine learning algorithms and workflows is quite a complex and highly skilled requirement sort of task. So at the preparation phase here, you have to collect what's called training data, you have to have world-labeled data, and that's really the foundation of then going through a process to build your machine learning model. When you come to build it, you have tools and sets and to use and specialist sort of people in that space. You need to choose which model to use, and that's a sort of specialist area its own right. You'll then go through iterative processes to sort of train and experiment and try out different algorithms. There's often debugging steps there. There's some debugging steps that are quite specific to the sort of AI domain. So the just general purpose debugging tools may not be as helpful. You then typically, when you're training, are you limited just by the training time on your sort of workstation, or do you offload that to a cluster? So you've got, again, specialist resources. And then once you've got a model, you want to deploy that, and that brings in where do you deploy it to, how do you scale that, how do you monitor that, and make sure it's still performing as expected over time. And that cycle then continues around. So that led AWS to the business case to build the Amazon SageMaker set of tools. So this is really an integrated set of tools to address this entire life cycle. So for example, within the collection and preparation of training data, we have a tool called a SageMaker Ground Truth. What this does is help you in that labeling process. So giving you tools to label data, either manually, semi-automated, or and semi-automatedly, or even offloading that to collections of other people or organisations to help you build those sort of training data sets. Once you've got that training data set, you'll then want to start building models and experimenting. So we have a SageMaker Studio, which is a Jupyter Notebook style environment to allow you to very easily have a hosted notebook to start experimenting, trying out those and doing that training. When you do the training, you can literally, via a single API call, offload the training step to a offloaded instance or even a sole set of instances. So you're not limited by just the compute available on your notebook, because often the notebook might be quite modest in what it needs. It can run on your laptop or a small EC2 instance, but you may want to cluster to run the training job as quickly as possible. We have specific debugging capability here that's aware of sort of the nature of algorithms to help you in this space. And once you get a model that works for you, you then have the ability to deploy to a production, again, the production set of instances. It can scale up and down based on the use of that model then to sort of maximise performance and minimise costs. We provide tools to monitor that algorithm so you can check that it's still performing as required and validate the predictions. And then when it's not, that'll flag to start iterating through this cycle. So as an example of this approach, I've given here, this is a link to one of our blog posts where we actually go through this step. We take some electro-optic imagery, we actually slice it up into what's typically called tiles, so you've got smaller amounts of data to deal with, pass that to some AI machine learning algorithm, and use that to do things like detecting building outlines and road networks. And these this kind of task can be performed automatically and releases the analyst to do more higher value-added tasks. So I'll just go through now a sort of typical bringing those together, the collection through to that AI machine learning implementation. So say I've got a satellite and I'm actually doing a collection and I'm looking for, say, shipping data from orbit. So you're going to go through a step of ingesting data, then some machine learning, and then, say, build an end-user application for people to consume. So ground station gives you the ability to downlink that data, demodulate it, get it into an S3 bucket, and you're starting to collect, say, images of the ocean here. What you'll typically do then, you'll take that, you'll use things like SageMaker Ground Truth, you'll use a set of that data, you'll find some images with ships and some without, use that to generate your training data set. You'll then use SageMaker Studio to with that training data, to build a machine learning model for, say, targeted at collecting and detecting those ships. Once that's working, you'll deploy that as an endpoint, so where you can pass new images to it and get an answer, yes, no, is there ships in this image? And that then allows you to start building some applications against that endpoint. So here it could be something really simple like an S3 bucket that says every time a new image comes in, yes, no, is there ships in that photo? If there are, you might trigger an alert to, say, a notification to some other system and log that to a database. And then if you want to be able to interact interactively, say put that up on a map, you might want to build a web app with something like AWS Amplify to have a user interface to that. So I've gone through quite a bit in this session, so just to sum up now, as you've seen, there's this huge growth in imagery and geospatial information from Earth observation, satellites, as well as other resources. And it's really, we're in this world now where there's more imagery than we have time to sort of look at ourselves. It's really driving that need for very high-scale storage and compute capacity co-located together, such as in the cloud. We've talked about how the cloud can be used across the whole intelligence cycle, not just in one particular part of that, and how automation can really start to help analysts to be able to focus on their sort of value-added tasks. So if that's inspired you to want to learn more about AWS, I'd just point you to our learning resources. So we have online 500 plus digital courses. And if you want to prove your skills in the market, we have certifications available to you. So thank you for your time now. And like I said, it's great to be here in person. Look forward to talking with you more over the day. And please provide your feedback. So this is a link to our survey. So we use this on all of our sessions to improve our content and direct what we do next year in other sessions. So thank you for your time.